Oh, hello there. Hey guys, what's going on? Memes here. And today we're not going to do anything fancy. We're just going to point out a particular relationship because I should probably I should probably shift. Ah, I'm not going to lie, I ended up like retaking an entire. Actually, no, I just ended up rewriting this so I could just use the same thumbnail so I could be on the other side. It was terrible. But so basically, if one has played around with a little bit of dimensional analysis, long story shorter, we have these things because of good old Max Planck. He gave us Planck's constant. Why? We needed to solve a catastrophe. Rumor is it was ultraviolet. And according to legend, got kind of frustrated. He's like, what do I need to make this work? And it was like, I don't know, like 91.5 nanometers or something like. He needed to put in a particular number, and then we just had a standard curve, and apparently energy was quantized in units of basically h bar. Maybe it's a half, maybe it's a whole one. I'm not a quantum mechanic, but it ended up taking a few more years to kind of figure out maybe what was going on. Like good old Einstein came along. It's like, we got photons and perhaps some Brownian motion. So perhaps atoms exist. Or whatever we conceptualize as atoms, some form of like a wavicle type of thing, according to, or at least within the general spirit of Matt Stassler, who wrote Waves Are Impossible Sea, who's I've had it recommended by a good number of folks on this Internet of Stuff and things. So I listened to it going across country. I think he did a pretty dang good job. Going to like all the equations like Professor Carroll does and the biggest ideas in the universe? Not really. Even you try something like a Higgs mechanism or Higgs Lagrangian and stuff like that. Yeah, there can be a bunch of terms. I digress, but the conceptualization is you got fields interacting with fields. There's some oscillation going on. There's different stuff on how they're interacting. Now, I'm not going to claim like I know all this is. I ain't no god nor prophet. I'm just a crazy person on the internet that is a gamer that I learn how to start playing a game. What's the first thing you do? Well, if you get any fighting game, what do? Quarter turn from down to forward punch. Why? Hadouken. What's the equivalent with this? When you just go on a Wolfram Alpha or use a Mathematica notebook and then basically just bring up all these things, see their relationships between each other. And within these three constants, you can create all the other Planck units, so to speak. Planck length, Planck time, Planck mass. Two more constants are required in order to get the Planck temperature and the Planck charge. That's Boltzmann's constant and the electric constant. Because once we get those +2 constants combining, we can form Voltron, I claim. Or at least we have the dimensionally measured ingredients of reality as we know it. Okay. It also happens to be 5 things, kind of like 5 lions or 5 Zords. Go, go, Power Rangers. I'm sorry. I like it. So that little metal riff, 90s kid. Oh, it goes. Welcome, Crypto. Good to see you, my friend. Good to see you. But okay, so we won't belabor the point. We'll go over to some basic, just how you can do this yourself, and maybe perhaps learn a little bit about what might be going on. Maybe get a little bit of elementary physics if you want there, because we're basically going to be going over a little bit of unit analysis, and you can just do these with the base units. You can literally, you want to get energy, you take your kilogram, you multiply it by your meter squared, you divide it by your time, the second squared. Okay, so what is that? Oh, mass divided, mass times speed squared, because you drive a distance. All right, you've gone a particular length. How much time was there? All right. Oh, maybe you're going 50 miles an hour, 50 kilometers per hour, or 100 kilometers per hour to try to maybe make it a little bit easier there. even though we have another factor of 60 rather than 60 seconds. I digress. The long story short is, well, if you're doing Planck units, those are just the limits of reality according to our current understanding within generally accepted physics. I know within the Wolfram Physics Project, Professor Wolfram and a good number of other people. And I am part of this because I did some calculations, and yeah, you get something at least far. Well, actually, that's an interesting thing now that I think about it, because a lot of the Wolfram limits are actually the limit, just kind of conjecturing what the minimum might be. Okay. Just even going through the thought process and thinking out loud, I suddenly, it reshapes things in your head. And even somebody just makes a comment and you're like, oh, my mind just tweaked in a different direction. Maybe that's a good thing. Maybe I'm just a crazy person. Who can say? Yes, Brian, I may not know karate, but I know crazy. Yes, Hadouken is actually perhaps an algorithm. These are okay. So growing up, I remember. Okay, maybe there were controllers that did this. But you got the turbo controllers because you could set them like auto or like full on. So basically, rather than having to push the same button a bajillion times, you just hold it down, and it would just send multiple impulses there and everything. Which for some things it worked, but then again, you still had to do all the other things with your controller and pursue. Dude, the folks that could pull off consistent spinning pile drivers with Zangief, power to you. Because I'm pretty sure that was like the move, and then like Balrog's full powered turn punch that could take about half your HP or your fighter's quote unquote status health bar, whatever. Yes. Quarter circle punch is the Y equals MX plus B of video game history. I don't have a counter to that. I find it hard to push back. I mean, I'm inclined to agree. If perhaps there's a, I'm not sure. I can't think of a better one at this point. So that's all I got. Oh no, more conspiracies. Welcome, Charlie. It's okay. Listen, maybe it's a conspiracy. Maybe it's a little bit of clickbait. Maybe it's all the deep state. What is the deep state? I don't know. Whichever individuals we can label as they, depending on our preference. I don't know. Some people maybe just prefer to keep their jobs. I don't know. I'm not here to house blame. At least we're not right now. Okay, so let's get into this. I got a notebook up and everything. All right, so let's go through this. Oh, the punchline is you just play around with these things. If you take hbar, this is literally just the Planck product. So if you take your three primary constructions, hbar, your C, your G, you're going to get like length of a sixth power divided by like seconds to the fourth. I don't know what that means. That has no dimensional correspondence, at least according to the Wolfram language. I like the square root because a lot of Planck constants are just square roots of things. We get basically, it ends up being equivalent to Planck length cubed divided by the Planck time squared. Which if you played around with constants for a while, you end up realizing that's basically just big G without the Planck mass. Or, on the other end, H bar C, the constant that base interpretation is bending stiffness, aka very often in your Lagrangian, if you're trying to have like an energy density or something like that, if it's raised to the fourth power or whatever it is, maybe it's just energy. I apologize. I haven't had some. Oh God, my files are all mixed up. I'm literally like the living embodiment of the mixed up files of Mrs. Basilie Frank Wilder. Maybe Miss. I apologize. I posted that because they're talking about a Michelangelo bust on and perhaps it being true in an art museum. I'm like, I feel like I read this book in like the fifth grade. We read it as a class as well. But I digress. So basically this whole thing, it's standard gravitational parameter, or let's just say it's the Planck energy distribution function based upon mass. whatever the heck that means. Okay, let's actually get it. I can share the thing. And all right. Planck Constructors. Okay, let's take a look at what the heck these dimensionful things are. So what is a dimension? We, as observers like us, to the best of my knowledge, we have a device, it goes click. It registers a thing, whatever that thing might be, whatever the magnitude may or may not be, detector goes click. Okay, we have an observation. I'm going to lean into we're observing actual things. Now, maybe we're not. Maybe we're not. Maybe, who knows? Maybe we're collapsing the wave function every single time, or perhaps just the wave function continues. Perhaps it's more of an ever ready thing. Maybe everything is happening everywhere all at once, or perhaps observers like us within our light cone, so to speak, whatever that means. It's our forward 90-degree projected direction throughout reality. Maybe we can't observe it. Maybe it's happening in another time and place, at least according to the observational perspective of observers like us, whatever may or may not be happening. I know I just caveated a lot of things. So here are our primary Planck constructors. H bar, so basically that's the reduced Planck's constant. This little thingy here. Hold on, let's get this little begging all this. Times 300. Here we go. So it's basically that H with a little squiggly bar on the top, going through the top of it. Okay. H bar, reduced Planck's constant. So what is it? It's Planck's constant of action. I actually kind of like the term Planck's constant of proportionality, because isn't that how Professor Planck ended up getting this? It was just like, what do I need to fit in to make it work? Well, let's see, it's going to work. It's a constant of proportionality. You happen to get for about the first 2 digits. We decided to divide it by a circle because it was working within a particular construction. Okay, so you could say, oh, maybe it's an elementary viscosity, because we also have an joule second. So standard interpretations. Angular momentum. All right, so a lot of times you'll hear H bar and you'll hear things like spin. Well, they don't actually have spin here, but some way say elementary viscosity. Okay, total angular momentum, action, angular momentum. One of the reasons why apparently this seemed to work is within classical mechanics, to my knowledge again, and I'm not a quantum nor classic mechanic. I've occasionally done an oil change, but my mechanic skills are limited. I wasn't a very good maintenance guy, but I digress. So basically, you just have the dimensions. It's like, well, it lines up with these dimensions. So these are ways to interpret it based upon Wolfram Alpha. Now, is there a particular interpretation that works better? Well, it might depend upon the hat you're wearing. If you're having a classical mechanics hat on, if you have a quantum mechanics hat on, heck, maybe you just have your tinfoil hat on and you go wherever you want. I usually wear it. I think it's some more aluminum foil. That's what we call it. But its dimensions are mass times an area divided by a unit of time. Okay. So you got to think of this. It's like you got a flat thing. It's got some mass. So you've got a massive surface and it's going by on a unit of time, or maybe you have a length, and now you got a momentum. Oh, wait a second. Momentum within mechanics? What's going on? Because momentum is this exact same thing, but it's not an area. It's your mass over a velocity. Or, yes, because momentum has to have a direction. So basically, if you have a mass traveling at a particular rate, it's got a speed. So a mass speed going in direction. I put a head of billiards ball. It's got some momentum. It goes, it transfers its momentum. It's in one place and then it goes to another place. Oh, maybe if it had those dimensions and it went a distance, maybe that's where the length squared comes from. I don't know. I'm just saying maybe these are reasons why we found this particular dimensional setup useful. Let's move on. C. All right, you can have all the different interpretations. Small c, the speed of light in a vacuum. That it's not necessarily quite a true vacuum. So apparently there's no true vacuum because there's the quantum fluctuations going on, whatever's happening. There appears to be a density to whatever doesn't seem to be there. So the vacuum itself seems to have an energy density about like 5.5. It's basically about a little under 3.5 giga electron volts per cubic meter. Well, that's a little under about the mass energy of 4 protons per cubic meter. I only know the first couple of digits because I've done a whole bunch of computations. So I can say words like that and kind of try to at least be, oh, maybe he knows what he's doing. I just seen it a bunch of times. It's kind of like if you played Pokemon enough time, you know which gym to go to, all the different trainers you need to go to, and it's like a video game. And again, it's knowledge of what's going on probably actually does help. So that's a unit of speed. What is that? A length. We travel a particular length or distance. We divide it by a unit of time. All right. I went 10 meters. It took me 10 seconds. I'm going 1 meter per second. You happen to be traveling a Planck length per Planck time. You're going at c, the speed of light, in a vacuum or the medium, in a medium, whatever that may or may not be. Okay, I know, what is it? The Science Asylum. Oh, God, I forget your name, my friend. But he did a thing. It's like, should we rename the ruler a light second, or should we tune it to light seconds? So long story short is it ends up being just a hair over like 12 inches or so, because this is about a meter is about 3.3 feet. So basically, if you divide the meter by this, you get it right about 12 inches. So again, it's one of the craziest things I ever heard at a political town hall. Very first gentleman got up and says, "Are you willing to lead the United States out of the dark ages and finally adopt the metric system?" And from what I could tell, the general discourse was everyone there was like, they had never heard that question. Even the candidate was kind of taking a little bit of back, like, I've never considered that. Doing a whole bunch of calculations, I'm going back. I'm like, that might not be the most unreasonable thing. Listen, you want to be an imperialist, continue to use a former British monarch's shoe size. It's totally up to you. Big G. All right. Newtonian gravitational constant. Yes, that's what we're talking about. And even though I talk about another big G, Godzilla, this is the Newtonian gravitational constant. All right. Where are we? Many things could be a character, could be a musical, could be a part. Ooh, which particle? Oh, the graviton. Yeah, we don't. Okay. It's got spin too, according to theory. Other than that, we apparently have no other idea what's going on with the graviton. Okay. It has never been observed to my knowledge. Maybe it exists, but apparently, at least according to Matt O'Dowd from PBS Spacetime, in order to measure a single graviton, so to speak, we would need to create a black hole because you need a wavelength down around the Planck length, and kind of by definition, reality shields itself. So, reality hiding in plain sight. I digress. All right, let's go back to the unit. So what the heck is this? This is, as we can see, it's 6.674. Gravity is hard to measure. Times 10 to the minus 11 Newton meters squared divided by kilograms squared. What the heck is that? Or it's times per centimeter cubed divided by grams squared. Okay, or if we converted to feet, we could do 3.44 times 10 to the minus 8 cubic feet divided by slug seconds squared. This is one of the fun things because there's I still enjoy the unit of the crab, which could also be measured in dietary intake, basically because it would literally be a portion of crab meat itself, or basically like a sunburn unit or something based upon energy flux density. Okay, long story short is, wait a second, it's got these dimensions. All right, why do these dimensions look familiar? You've got a length, so we got a volume here. We got a length cubed divided by time squared. Wait a second. Like I've seen this before. A length cubed divided by time squared. I realize it's the overhead light is literally. All right. Okay, no, it shouldn't be blocking. So, long story short, what is this? This is the Planck length. L sub P, the minimum unit of length or distance, according to physics as we know it. Maybe they're smaller, who knows? But basically, that's the limit to where our physics as we know it breaks down. We got a cubic length. We're divided by time squared. So basically, it's an acceleration. This is kind of why people say, well, gravity is a force. It's the curvature of space-time, because there's an acceleration there. Because force is mass times acceleration. What the heck is mass times acceleration? You got a mass. Maybe it's a mass all like me. Figure, okay, maybe it's 100 kilograms, whatever. You got a mass. You got to multiply that by acceleration. Acceleration. Okay, that's force. All right. I didn't do the R because that's for power. I learned that from home improvement. Force is mass times acceleration. We're just doing them Planck units, which are just one. See, that's the only reason I'm able to do any of this stuff, because you see the relationship that they're all going to just go back. If you see them enough times, it's just going to go back to familiar. It's kind of like back to forward punch, or so you do a quarter circle, or you do down to back and you do a kick or something like that. Maybe you do a sub-zero slide or something. It's just seeing the relationship between things. So there's a mass. Just mass and Planck things. We're just going to do the symbol, just whatever it is, Planck. M. We got sub P there. Planck mass. What's the acceleration? Well, number one, you need to, like in your car, you're accelerating onto the highway. So you need to travel a length. So you need to travel a length. In this minimal case, let's say you go Planck length. To an observer like us, your increments are going to be probably a heck of a lot larger. But to get the maximum force, this would be the force. Planck. I know. F sub P equals mass Planck, Planck mass times the length Planck, Planck length. And you need to accelerate, aka you get on the highway, you're accelerating. So over the course of a second, you're going to travel a distance. But that following second, you're continuing to accelerate. So each increment of time, you're going to be going slightly faster. So that's why it's time squared. So you get mass times the distance, and then each second, your time is going to be going up. So basically, it's like you're going at 10 miles per hour, 20 miles per hour, 30 miles per hour, 60 miles an hour, 60 kilometers, 100 kilometers per hour, whatever it is. As long as you are accelerating, you're constantly going a little bit faster each time. Well, that depends on how many. That goes to the third. It's called the jerk. AKA, if you're really slamming on, you're traveling cube, you got to jerk back. the acceleration. It's like, okay, all right, I'm feeling the acceleration. You're really cooking. Yeah. So basically, like if you're driving and all of a sudden maybe you downshift into something and you're going a little bit slow, maybe you jerk back and start going faster. Like, that's how I conceptualize this stuff. And well, maybe sometimes you need a jerk. I Nobody clipped that. So where are we at? Let's get back here before I completely lose myself. All right. Where are we? Is the end of the day we discover something big? Who knows? What gives me hope is there are smart people out there. Uh, oh no! Look, have you seen this guy? Well, talk about an oddball. I ain't even a spherical cow. I'm just like an oblong. I'd love to say gentleman, oblong gentleman. I ain't no gentleman. I'm a dick, literally. It's my middle name. Uh, I'm the hottest of the wall. Johnny's like, uh, going to out on me. I am the hottest of them all, except maybe the nice wolf lady Fizz. She's pretty odd, but it's all good. Who doesn't like Fizz? It's just an awkward celestial chibi wolf girl. I mean, what's there not to like? Oh God, I have no idea how she puts up with me. She's my longest surviving co-host. Oh God, it's terrible. Listen. I think that's why we get along because it's like, well, if we're all odd, maybe who knows? I feel like that's a personal resonance there between other human beings. I don't know. You'll hear folks say there's a Rupert Sheldrake, morphogenic fields and stuff. That sounds beautiful. I would absolutely love to that to be true. I have no idea how it actually works. I could see that being a thing. I just I just don't know necessarily exactly how it's a thing. I could imagine how it might be a thing. Uh, uh, all right, maybe perhaps it's all conjecture. So let's actually just go to the whole dang. So let's just do this. H bar. I don't even know if this is gonna work. Let's see. C times G. That was in a normal thing rather than alpha. It may not. Okay, so it's interpreting it correctly. So long story short is if you take the three primary constructors of your Planck units, you multiply them together, you get this number here. All right. What is this number? I have no idea. It has no dimensional interpretation. Here are the dimensions. Length to the sixth power, and then just time raised to the negative fourth. It's like, okay, well, what can we do with this? I don't know. Let's divide it by c raised to the fourth. That seems to be kind of a good metric at times. Let's see if it interprets it. Why is it going at c raised to the third? Okay, that is weird. That's this is 4, right? Why did it do it the other way? Oh, it's simplified. Okay. Because I'm like, it's giving the right answer. Why? Okay, so we had H bar, C, and G. I'm dividing by the speed of light to the fourth. Notice it just took out that C. Now it's just the gravitational constant times the elementary unit of action divided by C raised to the third power. And we get length squared. So the Planck area. That's what it says. There's dimensions of length squared. All right. Kind of cool. So I'm always a fan if I see meter squared pop out. I'm very biased on that. But okay, so let's not belabor the point. Well, if this by itself doesn't have a dimensional interpretation, let's take the root of it. Do the square root of all this. That's what we have. Here we are. Doing code there. Let's raise it to the 1/2 root, which is the same as square root. There we go. So we'll go through the different Planck units and correspondence and everything. Okay, so as you can see, so if we take the Planck constructors, or the base 3 Planck constructors, the Newtonian gravitational constant, h bar, the elementary unit of action, and c, the speed of light. If we multiply them, so we're getting the product. Product is we're multiplying them all together. We're taking the root product. Planck constructor root product. Okay. It's giving us, oh, wait, it's telling us it looks like gravity, except it doesn't have the Planck mass downstairs. Okay. All right, standard gravitational parameter. As we can see, yeah, we got a length. And since this is a -2 for the exponent there, that just means time goes down below. It's the denominator. Positive, it's on the numerator, kind of like this guy here. So we have length cubed. So that just means it's in the numerator. Boom, it's upstairs. Time is to the -2. That just means it goes downstairs. It's in the denominator. That's all. It's literally just kind of like adding and subtracting thingies there. So that's why it's easy. If you're not familiar with it, it's confusing as heck. You're like, why am I getting all these answers? I had a lot of awkward moments. I'm like, I don't know what's going on. And you put in time, you practice, you learn. That's the goal, to be less wrong. All right. Let me hydrate, because hydration is important. Okay. So that's what we get here. What is the consequence of this? Okay. We don't need it. All right. So let's take this whole thing and maybe we'll see this. All right. So we got all this jazz. Oh, hold on. Let's just do it that way. Square root. Because we can. Boom. There we. All right. Wow, it's telling us straight there. Yeah, square root and big G H bar C. Yeah. This number is okay. Hold on. Gravitational parameter. Okay. Here's what I'm saying. Scalar energy distribution function per mass. I mean, to be fair, that is kind of what gravity is, right? Because apparently, like, the curvature of space-time is directly related to like the mass in it. The mass seems to induce curvature. Why? I don't know. Magic, gremlins, whatever the actual mechanism of gravity may or may not be. It's basically a scalar energy distribution function per mass. So that, I mean, again, this is a dimensional interpretation. And all we're doing is literally, as we can see simplified here, we're just taking 1 square root of G times the square root of H bar times the square root of C. Wait a second. This reminds me of something. For those of you that have been following my madness for a particular while, this may ring a slight bell, because it's starting to ring a bell in my noggin. Hold on, give me just a moment. I feel like there might be somebody that expressed the importance of radicals. All right, let's share with the class. What do we have here? What am I doing? Wrong buttons. All right. All right. So I just typed in radical. Oh, wait a second. Here's a video from Rick. He was explaining to me radical powers, and we actually zoom in a little bit. Wait a second. We're constructing things with the square root of c. Let's can see at least the square. Oh, wait a second. Those are square roots over there in that chart. Huh. Maybe there is something interesting going on here.
The thing says we're live. Hey guys, what's going on?
Okay,
Today we're bringing you a very special presentation titled "Radical Powers" by Physics Monastery Fractal Faculty.
Yes, Rick is fractal fact. Okay, so long story short is Rick was saying that maybe there's something interesting going on when we look at things like radicals. Okay, yep, square root c, square root my terrible h bar there, square root g. Okay, we got Boltzmann's constant, all right, Coulomb's constant, and elementary charge there. Okay. Huh. And yep, that's it. You can write those powers in that way. And we're going through the different things. All right, Planck force, Planck acceleration, Planck energy, all that jazz. Huh. Well, that's interesting. I don't know if it's related. Then again, of course, I'm like, well, all I did was just combine three and just take the root of that. And the same thing is basically just taking those, right? It's because that's what the document tells us. That's what Mathematica is saying. At least I don't know. Is my notebook lying to me? Oh no. Who knows? Who knows? Maybe it is a particular thing. Okay. I'm just saying that, well, Rick has already talked about this. It appears it sounds like standard gravitational parameter, but like there's no mass involved. But depending on where you put the mass, scalar energy distribution function per mass. What might that mean? Why is it not just a standard gravitational parameter? Well, let's see, shall we? Take the square root again. And now let's do this. Let's divide by the Planck mass because we can. Okay, so it's the exact same thing, just the square root of all those guys, divide by the good old Planck mass. What's going on? Oh, it's running, querying the database, running. Then like that. Okay, let's just change it to the alternative explanation. Should have just done that from the start. All right, square root of all that jazz. Why with a Planck mass? Oh, look. This number looks 6.674 times 10 to the minus 11 meters cubed divided by kilograms second squared. Oh, our good old friend, the Newtonian gravitational constant. Friend. Oh, we deleted our friend. Not IRL. Just well, that's what it is. Because it also says the Newtonian gravitational coupling, aka just like on our little thingy, it comes out exactly what we expected it to be. We're just dividing by the Planck mass. How do we divide by the Planck mass? Well, if we just literally do let's just do this. We want to make it look at least a little bit prettier and a little less like a crazy person. Just a little. We do 1 over the Planck mass. Okay. So since it's outside, maybe we put our little protective brackets on just so we can tell exactly where it is. So we're dividing by the Planck mass. What do we do here? We literally just write the Planck mass. Bada boom. 1 over it means you could write to Planck mass raised to the -1. Just means it goes downstairs and then it just goes downstairs there. Boom. You get your big G. Why? Because that's by definition, it's literally made of these components. 3 dimensions of length divided by the dimension of mass times time squared. So it's literally due to the curvature of space-time, mass seems to accelerate things because it begins with a gravitational well. Yeah, accelerate. Yes. H bar C to the G, baby. God. We should just get some C dance and just use a whole bunch of maybe slowly up for, I don't know, what do they say? Public release. God, I saw a horror Jiminy Cricket earlier. It was terrifying. But I digress. All right, where are we? Big money, no whammies. Okay. So, all right, we divided. What happens if we do the other thing? What happens if we multiply? Okay, same thing. We take the root of our constructors, and this time we just literally just write Planck mass. Now we're gonna multiply. Why? Because we just divided. So we might as well do the thing, right? Okay, I got confused. It moved the notebook up. I'm like, we just did the divisions. Okay, now we're doing the multiplications. What do we get? We get this number here. What does it mean? Well, let's continue down. You're going to notice some very interesting things. Well, it already has an associated unit. It is the reduced Planck constant speed of light product. Because that's what it is. It's h bar times c. Okay. As we can see, that's just 1 over 2 pi. Because, well, if you were to take Planck's constant, Planck's reduced constant is just Planck's constant divided by 2 pi, or a circle, or a cycle, if you would. Or 10 to the minus 26 joule meters. Well, a joule second is action. So a joule meter is bending stiffness. Gravitational acceleration, bending stiffness. Oh, this is the thing that you help divide into energy in your Lagrangian. So if you got like 4 dimensions of energy, you divide it by like h bar c raised to the 3rd power. Yes, I learned that as I had chat walking me through the very basic elementary stuff on Lagrangians. I'm like, oh, you put this here, you do this here. I now see why physicists said a lot of these things just equal to 1. Because otherwise, yeah, constants here, you get constants there. Although, who knows? Maybe something is deeply hidden. Perhaps you will be the one to find it. Or have found it. Who knows? I ain't Santa Claus. I can't keep track of everybody on the planet. So basically, it's the exact same thing. 3 dimensions of length. So a volume divided by an acceleration just with mass upstairs. AKA, we literally just go from this. Oh God, of course. Yeah. This is my own bare hand because I'm a savage. Not really. But if Wendy's didn't exist, I'd probably be screwed. All right. All we're doing is we're removing the 1. We're just multiplying it by the Planck mass. Okay, so what happens over here You have our same dang expression. It literally just goes up. Blank. Boom. All right. That's just hbar c. If you're curious of what's happening here, okay. If this is hbar c and big G is equal to the exact same thing, Planck length cubed divided by the Planck time squared. You got Planck mass over there. Okay. But you kind of see what's happening. These are the exact same thing. The only difference is the Planck mass. So when they come together, of course, it's going to cancel out. Just because it's like you got the Planck mass up there. The Planck mass is down here. Those cancel. Bada boom. You got, oh, this is supposed to be squared. Apologies. Lying to everybody. So you got this thing multiplied by this thing. It's the same thing. And you take the square root. That's why you get that. That's all. Simply applied algebra, or what? Here's the thing: you just did y or x. I'm just going to be like, okay, I can kind of follow, but I just don't retain it. It's like, okay, that's a thing. I understand how it works. Now I need to use this effort. You play around. It's like, oh, I'm literally just describing magic words or runes or something. I was a big fan of playing dwarfs when I was playing Dungeons and Dragons, so runes and stuff kind of resonate with me a bit. That's all. Okay, so let's actually just go through a thing here. All right. Un momento, por favor. Let's do this. Okay. So I should probably bring up the other thing, because I did leave the link to the Planck constant thingies. Where was that? Planck units. There we go. So I have it. All right. There. Hold on. All right. Now we can. Okay. So let's do this. All right. So we're here. Cool. So let's do this. Get this over here. We got our notebook over here. So let's share this. No. Would you like to leave the studio? Oh, don't get me tempted. No, we got to go through our derivations, because we said we're going to do a thing. We should do a thing, right? If somebody finds this useful, the goal. All right. Share the whole kid and caboodle. So hide ourselves. Yep. Don't look at my thing, bro. All right. So I got this. All right. The long story short is, all right, we got our Planck length there. And these are the modern scientific values based upon what friend Max Planck had originally gone through when he was just relating these things. So you just go square root like a lot of these things, and all we do is h bar big G divided by c raised to the third power. And enter our interpretations. Okay. Oh, okay. I got confused. It popped us back up in the middle. Yeah. So as we can see, all right, we got one Planck length that lines up. Or some may say it quote unquote cuts the unit. I don't know. I like Force and Fire. That series is pretty good. Planck length. We're just computing it. The square root of the elementary unit of action times the gravitational constant divided by the speed of light cubed. We're just taking the root of that. And that root gives us these numbers over here. We can see we get those numbers over there to the error bars and rounding up just a little bit there. But that's what we got. All right. So the Planck mass, as we can see, we do the exact same thing, except we're moving some stuff. You see what's going on here? Yeah. We got the square root. This time, h bar remains up top in the numerator, but we're bringing the speed of light up. Oh, so if we remember to about 3 minutes ago, we're just doing that thing. Because remember, h bar c and big G are, it's the same thing, except one is mass upstairs, one is mass downstairs. All right. And when you divide them, that means the mass downstairs, everything cancels out except the mass downstairs ends up going upstairs because it's already downstairs. And then when you're dividing, it's like multiplying. I know this is why I got confused back in middle school. And then you go through it enough times, it just kind of gets drilled in like a lot of other things. So, what do we do? Okay, so our output. So basically, it ends up being the Planck mass squared, but we're taking its square root. So we get, hey, aka, it's the Planck mass. That's what comes out, literally also by definition. All right. So we continue there. The interesting thing is, with the Planck mass, the only one where they're all at the same power. Or at least for that construction. Maybe that's telling us something. I don't know. Maybe it's Maybelline. Trying to make a Maybelline joke there. Again, we just do the same thing. We take the square root of h bar g. And again, this time we're dividing by the speed of light raised to the 5th power because we can. And this, by the magic of computation and the Wolfram knowledge base, is going to get Planck time. Why? That's the next thing on the list. And by definition, that's what it gives us. 5.391 times 10 to the minus 44 seconds. Very short duration of time. Not nothing, not infinity, just an incredibly short interval. That's what it is by definition. Now, here's where we start getting a little funky. The Planck temperature. This is where we need our 2 additional constants. This first constant we're going to need goes by the name of Boltzmann's constant. Okay. Ludwig von Boltzmann was a gentleman so far ahead of his time, like literally he was one of the, okay, I can't say the first because it's probably Democritus postulated that perhaps everything was made of atoms or elemental minimums there. Boltzmann was the dude, man. It's like, all right, statistical mechanics, we look at this, what is the configuration of all these microstates? He earned a constant. He was also bullied so severely that unfortunately the man ended up taking his own life. And then apparently that happened to the next person that was embarking on, was it the Ehrenfest? Was embarking on the quest of statistical mechanics. He ended up losing his life by his own hand as well. And then the continuation of the book says, now it is you, dear, the reader, who can continue the quest of statistical mechanics. It's like, oh. Yeah. So Boltzmann's constant, what is it? That. Long story short is we need that to get convert from energy to temperature. So it also helps give you entropy of things because that's its definition. It's basically energy divided by a temperature component. So long story short is we need that in order to make things work. So again, square root of h bar c. Speed of light to the 5th this time. It's on the numerator. We divide by big G. And now we need Boltzmann's constant squared. Why? Well, we're taking a square root and we want one dimension of temperature. So we're only inputting one dimension. We're going to get the root of temperature. And that usually doesn't make dimensional sense. There are some interesting root. Well, we'll get to that later. It's not for the course of this thing. So Boltzmann constant. Like literally like casting a magic or writing a scroll for a spell. At least that's how I like to think of it. All right. We got all that. Let's get our definitions. Go down there. So bada boom, bada bang. All right. There we go. We got the Planck temperature. All right. 1.416 times 10 to the 32 Kelvin. Very often you'll hear folks say that Planck units, oh, those are the minimums of stuff. I think better phrasing is limits of stuff as we know it. Why? I think a minimum temperature, that's a maximum temperature, my friends. If it was like this, we would be, okay, if this room is a Planck temperature all throughout it, I don't think we would be having this conversation. You try to shove that much temperature of molecular stuff into a Planck volume, you know, you're in a black hole. Whatever that may or may not be, and again, I'm a I prefer the basis of mass hole. I think that's more a little accurate there. Coupling means in physics is just how things work in react. I mean that maybe. All right. Here's where we get on to certain conventions. And again, it depends on how you might feel about this. I prefer using the Planck charge as this. You can do it as this. So long story short is it's whether I think is it literally a difference of 4 pi? Yeah, it's just literally a difference of 4 pi. But the Planck charge. Notice this is the only one without any gravity involved. There ain't no big G in there, so maybe that's telling us something. So for the Planck charge, we're gonna again do square root of 4 pi. That epsilon naught, that's the electric constant. Trick constant. So this is the second constant that you need. So you could use that. You can use Coulomb's constant. I think that's technically the difference there. But basically, you need something with epsilon, the electric constant there, and Boltzmann's constant, and then you can basically make all the other units of stuff and things. And then we had that. All right. We get enter. We get our definition. Where are we going? Got all that jazz. And I'll keep pumping us up. AKA, we get units more. This is the interesting thing. It doesn't tell. Okay, yep, there it tells us. The Planck electric charge. Yep. Because we got all those. And then all our derived units. Okay, so these are the. So this just here, as we can see. All right, let's just go through them real quick. All right, so we got h bar unless your unit actually has a gravitational constant divided by. Oh, wait a second. Isn't there something about mass or something there? Oh, no. Get our interpretation. All right. Oh, no, that was linked. That gives us. Oh, look. Area. So we get the Planck area. All right, cool. Our next one, volume. Okay, so you could either do 3/2. Well, that was kind of 3/2, so that seems a little musical. No, let's just do it in the original. We'll keep doing the square root. Square root of h bar g. We got to raise that one to the 3rd. And we divide it by light. raised to the 9th power because, well, of course. These are just the dimensionally identifiable things that come out when you mix all these units together. So as you can see there, now we get a volume, Planck volume. All right. Planck momentum again. Square root of h bar c raised to the 3 divided by our friend Big G. You can tell. I spent far too much time going down Wolfram holes and just playing around. Okay. And that gives us the Planck momentum. Why? Well, it's momentum. Because that's what it says right there. It's going through. Momentum or impulse. And since it's in Planck units, coincidentally, this is so basically this is about 1.5 times the soccer ball traveling. So basically, if you ever got hit by a really well placed kick, you deflected a soccer ball. It's in the realm in which we live, which is kind of interesting. So because the Planck mass is 10 to the -8, and given our unit convention, Planck speed, aka speed of light, is 10 to the 8. So they kind of end up at the first power or at this scale. Okay. And then energy is the square root. H bar c raised to the 5th power, and then we divide by big G, and we take the root of that. We get our definitions, and then force. A big thing from Dr. Salvatore Pais. We got the Planck energy there. All right, now let's go to the Planck force. Planck force is, we don't even need roots here. So the interesting thing within the Wolfram Physics project is the things that were square rooted, we could kind of translate for, but some of the things that weren't square rooted, like long story short is I think for the Planck power, I wasn't getting what seemed like a minimum. And there was we're taking the square root of the dimension of flux, using it as a number, or at least that's what I was doing. And for some reason, the unsquare rooted things didn't really seem to work. I needed to take the unsquare rooted things and of another value. I don't know. I haven't done enough analysis on that that was just like literally just a quick footnote. Units. Okay, so of course it gives us the Planck force. All right, and now Planck density. We're kind of doing the same thing again. Just hit enter. And a little mathematical notebook. Speed of light raised to the 5th power divided by h bar. And now G2. Elementary unit action divided by the gravitational constant squared. Okay, we go through that. Boom, Planck density. 10 to the 96 kilograms per cubic meter. That's basically if you filled up every Planck volume with a Planck mass density. And now we go back to our acceleration, which we did over there, and that is the square root of a speed of light raised to the 7th power divided by h bar, gravitational power. Boom. And after all was said and done, and I finished lagging out, get our interpretation. And there we are. 5 times 10 to the 51 meters per second squared. Acceleration. Long story, you also need like a 2 pi to actually get you up to the Planck temperature there. So do you get the full cycle of acceleration? Okay. Save. We'll save that to cloud just because we have it there. And it's an example of things that maybe we could do someday. But that's about all. We got constructors. Save. Okay, and I guess if anybody wants this notebook, hold on. Just in case, file, publish to cloud. What do you want? Swanee cloud. Oh, wait, I realize I haven't even been sharing that screen the whole time. Wow, nobody believes me at all. So terrible. This is what happens when you hide yourself. All right, so publish. Go there. Okay. No, my potential tutorial clip down the hatch. It's okay. Maybe I should do something more formalized. Does this not want to publish to the crowd? Oh, it's freezing. It's freezing. I tried to do too many things. It's okay. We saved it. All right. Let me quit out. Grab ourselves a reopen. Maybe it won't. There we go. Planck Constructors. All right. Enable dynamics and file and there we go. Maybe I angered the cloud. Oh, I think I need to exit the kernel. Yeah. All right. Well, we'll save that for later. I'm gonna belabor you with like. Yeah. Of course. All right. Probably had that same kernel running for far too long. All right. There we go. So that's about all we got. I know. Yeah, just little interesting coincidence and everything. Hey, Zaka, what's going on? We are just literally wrapping up. I'll try to. I was going to publish the notebook in the chat just to follow along. It was just basic dimensional analysis, the definition of Planck units, and basically kind of stuff like this. I was just going through like kind of how it worked, and just it's just units canceling out. So that's no, it's nothing special. It's just very interesting that. Wait a second. I think the square root of h bar c and g, basically you get 3. You get Planck length raised to the third, divide by Planck time squared, which if you put the Planck mass down in the denominator, you get the gravitational constant. You put in the numerator, you get h bar c. So that's why, for instance, for the Planck mass, it's literally just h bar c divided by g, and you take the root of that. Why? Well, you already get the Planck mass in the numerator. You got g downstairs, and you're dividing into it. And the mass is already downstairs, so you're dividing a divisor. So therefore, it multiplies. So basically, you just add the Planck mass. You don't add it. You just add an exponent. So it goes from Planck mass 1 to Planck mass 2. You take the square root, aka you get the Planck mass. I realized without watching it, that was just a whole bunch of words and everything. It's like, you trust me. Don't trust me. Verify. But yeah, that's about all we got. I gotta go make some dinner and stuff, but yeah, I think there's gonna be some interesting things going on. And again, if anybody wants to take part in Kurt Mungel's Core 1 contest, you need a voiceover, you need somebody to pitch an idea to. Don't have infinity time, but I'm happy to try to help out folks that would like to share different ideas and maybe help move humanity forward a little bit. But oh God, don't trust, verify. I'm usually wrong, but every once in a while, crazy people notice things too. With that said, take care of yourselves all. It's a wacky and wild world out there, but it's open for a better tomorrow. Peace out, everybody.